All life on our planet is supported by it. Approximately 66% of our body weight is made up of it, and every system in our body depends on it. Safe water is a vital part of our daily lives. The state of Maryland is defined as much by its waterways as by the geographic boundaries of its land. The extensive coastline that edges the Atlantic Ocean and the Chesapeake Bay is riddled with rivers, bays, and creeks that merge with other bay tributaries. For those that make their living working these waters, and for recreational users as well, protecting these waters is critical, which is why water is so important. That is where you come in. Ensuring that our drinking water remains safe is vital as well. Your role is crucial in helping to maintain our quality of water and quality of life. The periodic water sampling you provide is key. The Safe Drinking Water Act and associated regulations provide the guidelines we need to do our job effectively. The SDWA was passed into law in 1974. It was later amended in 1986 and again in 1996 to include protection of not only drinking water, but source water as well. The Maryland Department of the Environment is responsible for the implementation of the Safe Drinking Water Act in Maryland. Our drinking water can come from many sources, such as wells, groundwater, streams, rivers, springs, and lakes. The protection of these sources has become increasingly essential in providing Marylanders with safe drinking water. To make certain we remain in compliance with the SDWA and maintain quality drinking water, periodic sampling is required. To help maintain your expertise in this critical position, this presentation will guide you through the process of water sampling step by step, beginning with the variety of water systems you may encounter. There are two main types of water systems, public and private. A public water system is one that features 15 or more service connections or 25 or more individuals for at least 60 days per year. Within a public water system are two subcategories. The first is a community system, which is a year-round residential. The second subcategory is a non-community system. Within this subcategory, you may find two types of non-community systems, transient and non-transient. A park, campground, or a rest stop could be classified as a transient, non-community system. A school, daycare, or office building would be classified as a non-transient water system, since it serves 25 or more of the same persons at least 6 months out of the year. Private water systems have fewer than 15 service connections and less than 25 individuals for at least 60 days. An individual home well, a small business, or a small shared water system could be categorized as a private water system. When your samples are taken and delivered to the laboratory, there are 4 sampling parameters that are tested in the drinking water: bacteriological, physical, chemical, and radiological. Testing for all of the bacteria, parasites, and viruses that could be present in water would be difficult and expensive. Instead, total coliform is measured as an indicator. The presence of coliform bacteria in water suggests that there may be disease-causing agents in the water. The second category of parameters, physical, generally is associated with taste, odor, color, pH, temperature, alkalinity, and dissolved and suspended solids. These tests are done primarily in response to a complaint or concern, or to confirm water treatment performance. The third category of parameters, chemical, includes the testing of inorganic compounds, IOC, metals and organic compounds, OC. Inorganic compounds can include fluoride, nitrates, and nitrites. Cadmium, copper, arsenic, lead, and mercury are a few of the metals sometimes tested. Organic compounds are divided into 2 categories: volatile organic compounds, VOC, and synthetic organic compounds, SOC. VOCs may indicate the presence of fuel, solvent spills, or leaking underground tanks. SOCs may indicate the presence of pesticides or herbicides. SOC testing is performed annually for surface water systems. Protected groundwater systems are placed on a reduced monitoring frequency of up to 12 years based on the statewide waivers. The final category of parameters is radiological. Gross alpha radioactivity, radium-226, and radium-228 are generally tested. For systems with gross alpha levels over 15 picocuries per liter, testing for uranium is also required. There are different collection locations for the different kinds of samples. There are three main sample locations: source water, point of entry to the distribution system, and within the distribution system. Source water sampling is required by the Surface Water Treatment Rule, SWTR, the Groundwater Rule, GWR, and also prior to issuing a certificate of potability for wells. Point of entry is a sampling point after treatment and storage, but prior to the branching of the distribution pipe. The point of entry is the point where treated water enters the distribution system. Distribution samples are taken within the piping system that serves individual service locations. Some things to be aware of when sampling from private homes are point-of-use POU treatment devices, water softeners, UV disinfection systems, and filters attached to a kitchen faucet. These are all examples of POU treatment devices. Samples are not to be taken from such devices as they may not represent the entire water system. In fact, activated carbon devices may even harbor bacterial growth if not changed on a regular basis. When sampling bacteria from a private home well location, the first thing to do is to flush the tap for 6 to 9 minutes. For a public water system, flush for a minimum of 2 to 3 minutes. This will help to ensure that the sample will be representative of the system. Flushing allows for the most accurate representation of the water system, as the water will be below the frost line rather than sitting in the system. In Maryland, water below the frost line will be within a degree of 57 degrees Fahrenheit. The common samples taken from this location will be routine bacteria samples, which should be taken from a tap in the distribution system, usually in a bathroom sink. Kitchen taps should be avoided for bacteria sampling due to their proximity to food preparation, a potential contamination source, and the fact that there are usually mixing valves and swivel taps with aerators, all of which should be avoided for bacteria sampling. At times, a special purpose raw water sample may be needed, due to a change in property ownership, to determine if groundwater is under the direct influence of surface water, as an original well sampling requirement, or due to damage to a well. The sample should be taken as close to the well as possible. Not all homes will have a tap before treatment or storage, so a tap such as a basement laundry sink or an outside tap may be the closest access to the well. Lead and copper sampling is a special type of distribution system sampling. Samples are collected as the first draw of the day from an area tap used for consumption, like the kitchen sink. This location is ideal because it is where most water for cooking and drinking will be drawn. Some public water systems may have a backup water supply well. This is used to give the main well a rest, or when repairs are taking place, or when the groundwater supply is low. If a backup well is present when sampling for VOCs, IOCs, and SOCs, a point of entry sample must be taken at the point of entry of both the primary and secondary water sources. Be sure to clearly label the sample to identify which entry point it came from.
You will need to know the required equipment to properly collect a water sample. Keep in mind, not every piece of equipment will be used for every sample type. In your equipment kit, you should have the following: a cooler for shipment and transport of the samples, ice for the cooler, a colorimeter, and reagents for testing chlorine residual, a pH meter with calibration buffers, nitric acid, sulfuric acid, PVC or unsupported neoprene gloves to prevent contamination of samples, safety goggles or glasses, sample containers of various types and sizes, laboratory slips, labels and markers for sample identification. There are also some additional items that are recommended, such as paper towels to clean the outside of your sample containers and plastic storage bags for the samples. Safety may seem like the last thing you have to worry about when gathering your samples, but you can never be too safe. Some containers, depending on the sample type, may contain a chemical agent or liquid preservative such as sodium thiosulfate, nitric acid, or sulfuric acid, which can cause burns. It is important to handle such containers with care and caution. This is where your neoprene gloves and safety goggles are put to good use. Check to make sure you have the appropriate personal protective equipment for the sample containers you are using. Hygiene is another concern when taking samples. Prior to handling your container and collecting a sample, it is recommended that you thoroughly wash your hands. Also, food, drink, and secondhand smoke have the potential to contaminate your sample and cause false lab results. Do not wear perfume, fill your car with gas, or use hand lotion if collecting volatile organic samples the same day. Proper hygiene cannot be stressed enough. You have all the proper equipment to take your sample. You know how to safely collect the sample, including how important hygiene is. It's now time to actually take a sample. When collecting your sample, you should routinely test for chlorine residual, pH, and temperature. These can all be done in the field. For collecting a bacteriological sample, there are 10 basic steps that you need to follow. Select an approved sampling location if any have been designated. In a public water supply, the sampling locations are designated in the sample site plan that has been reviewed and approved by MDE's water supply program. Each representative sampling location is typically located in the distribution system and is usually considered accessible during the day. Examples include hospitals, city buildings, pump stations, restaurants, and dedicated sampling stations. Sampling sites specified in the sampling plan should be selected carefully throughout the distribution system to represent the varying conditions that occur throughout the system or plumbing. It is especially important to identify and include in the sample site selection those areas that may adversely affect the microbiological quality of the water. In restaurants, these include high-use areas such as faucets at waitstaff service stations, bathroom taps where the consumers make contact with the water, and sinks in food preparation areas. You should also consider areas of potential cross-connections, varying population densities, low pressure zones, sites of deteriorating water lines, shared connections, dead ends, areas of low velocity water movement, and other trouble spots in the distribution system. Faucets and specially installed sampling taps are the two most common types of sampling sites. Each faucet should be examined carefully to ensure its suitability. Poor faucet design or placement may contribute to invalid sample results or fail to identify problems within the distribution system. Some examples of undesirable faucet conditions are swivel-type faucets that have a single valve for hot and cold water, faucets that have leaky packing material around the stem, faucets that supply areas where bacterial contamination is likely, such as janitorial or commercial sinks, faucets close to or below ground level, faucets that point upward, such as drinking fountains, faucets that have threads on the insides of their spouts, outdoor frost-proof faucets, and faucets that have aerators. If such faucets are to be used, the aerators must be removed before a sample is collected. To avoid the problems inherent with faucets, some water suppliers collect water samples for coliform analysis from special taps connected directly to distribution piping. These special taps can be simply a faucet at the end of a riser pipe connected to the distribution line or a more sophisticated manufactured sampling station device. Remove any aerator, strainer, or hose that is present. as these may cause false positive coliform sample results. In the past, some sampling practices involve spraying the tap with a chlorine or alcohol solution, or even flaming the tap. However, this is not recommended by EPA or MDE, since many people believe this practice kills attached bacteria and may create a sample that is not representative of the water system. Samplers should take care not to damage the tap or surrounding areas with harsh chemicals or flame. Turn on the cold water and run the water to flush the tap. This typically takes 2 to 3 minutes. While the water is running, fill out the labels, tags, and laboratory forms. Apply the label to the container. Then, reduce the flow that the stream is no greater than 1/4 inch in diameter, or about the width of a pencil. Check for the steady flow. Test for both free and total chlorine residual and the pH of the water, and write the results on your lab slip. Then position the bottle under the water flow. Hold the bottle in one hand and the cap in the other. Do not lay the cap down or put it in your pocket. Water dripping from your hands can also cause contamination of the sample, so extra care should be taken when collecting this sample. Fill the bottle to the shoulder, or about 1/4 inch from the top, ensuring that you collect at least 110 milliliters and there's still some airspace in the bottle. Many bottles have a 100 milliliter fill line, but the lab needs an additional 10 milliliters to test for the presence of thiosulfate. Be careful not to overfill the sample container because this will wash out the thiosulfate. If this happens, discard the container and use a new one. The sample container should be tightly capped. Shake the sample if necessary to dissolve the thiosulfate. Blot the container off with a paper towel to dry it. Since ice is usually required for shipping, it's recommended that samples be bagged separately in plastic bags to eliminate any contamination of the sample. Turn the tap off, replace the aerator, strainer, or hose. Double check that the information on the label matches the laboratory form. Complete any additional laboratory forms that came with the sample bottle, including chain of custody forms. Then place the sample in the cooler. The samples must reach the laboratory and analysis begun within 30 hours of collection. It is recommended that all samples be maintained between 4 and 10 degrees Celsius. If the laboratory is not nearby, send the samples overnight by U.S. mail or by courier. If the laboratory has any additional shipping recommendations or requirements, they should be followed closely.
Paperwork is a critical part of the water sampling process. There are a number of different forms that must be completed depending on the type of sample collected. Complete all laboratory forms that come with the sample bottle clearly and legibly, including the chain of custody form. Be sure to clearly identify the system information, like the Public Water System Identification Number, exact sample location, date and time of collection, and the sampler's name. If the sample collection point has a specific coded identification, include it on the form. Remember, sample results are only as good as the information that makes them legally valid and explains their meaning. There should be enough information on your record for someone to find the exact tap where you took the sample.
It's important to test your drinking water in order to make sure it is safe and free from harmful contaminants. There are several federal drinking water regulations in place that ensure the public drinking water systems test the water on a regular basis. There are many contaminants found in drinking water. These include bacteria, and the indicated organisms there are total coliform and fecal coliform. Inorganic contaminants, which include nitrates and metals. The synthetic organic contaminants, which include pesticides. The volatile organic contaminants, which include petroleum products, and also radiological contaminants, which include gross alpha. The role of MDE is to enforce all federal drinking water regulations under the Safe Drinking Water Act. If a problem arises, MDE will act quickly to ensure Maryland's drinking water remains safe for all of its citizens.
According to the Mayo Clinic, the average person needs to consume about 2 liters of water per day. To put things into perspective, the 2009 Census Bureau reports the population of Maryland is approximately 5,700,000. That comes to at least 11,400,000 liters of water consumed at a minimum each day. The World Health Organization, WHO, estimates that each dollar invested in water treatment has an economic return of anywhere between $3 and $34, depending on the region and the technology employed. So you can see that what you do and how you do it is of the utmost importance. Take pride in knowing you are helping to provide quality drinking water not only to family and friends, but to millions of Marylanders. It is one of our most precious natural resources. Our bodies, our minds, and our planet rely on it. Water. Pure and simple.